feedback and coevolution of black holes.
All right. Well, at the risk of sounding repetitive, of course, I want to start by, again, thanking the organizers. It's really a tremendous honor to be here, to be invited to speak beside so many people that I have so much admiration for. And in particular, there's so many people in this room whose ideas I've shamelessly stolen that I'm a little bit nervous. But hopefully, those people will be happy with how those ideas are being run with. Or if they're not, it'll at least generate an interesting debate. So I'm just going to give a fairly broad overview of the state of theory about feedback from black holes. And it's something we've heard alluded to a lot. Just now, Marta started getting a little more into the details. But of course, the overview, the sort of motivation for AGN feedback, I don't think with this audience I need to spend much time on. But of course, just to mention it, we've talked quite a lot about how nearly every massive galaxy hosts these giant black holes. And from the Sultan argument and its modern variations, we know, and also from more direct observations like what Juno described, that much of the mass is accreted in some short number of bright episodes. So that suggests that these violent episodes are actually integrally tied to the mass in black holes. And of course, we know that the mass of the black hole is tied closely to the properties of the host galaxy. So this is just one example of the M-sigma relation, which to the extent that it's true at more than one redshift would imply strongly that black holes and bulges co-evolve. Now, of course, on the theory side, when we see a relation like this, it encourages people to run with it and use it to solve all sorts of crazy problems, as Lewis mentioned in his talk. And there's a huge number of problems that theorists have invoked black holes to solve. Some were problems in search of any source of energy that could help them. Some were problems that people had long suspected black holes played a role in. So one, for example, most commonly cited in models of galaxy formation is explaining the massive end of the galaxy mass function. So this is, black is the observed galaxy mass function. The red line is what happens if you run a model with the very best you can do at present day, or at least close to it, incorporating the physics of stellar feedback, but ignoring any feedback from black holes. And what that does is if you have no sources of feedback pumping energy into the ISM, you grossly overpredict the masses of galaxies at all masses. If you invoke very strong feedback from stars and supernovae blowing gas out of galaxies, you can solve more or less this problem at low masses, but it really just fails for all the sources of stellar feedback we think we understand at high masses. And there's related problems too. This is not actually the same problem as explaining the colors of galaxies and galaxy quenching, which is that even if these galaxies are not growing so rapidly, they should be accreting out of their hot halos at a rate that would power star formation sufficient to make them too blue. Essentially, that's just a modern variant of the cooling flow problem, which keeps coming up in different forms. And there's many other issues that we want to understand. For example, why did black holes and galaxies form at the same time? This is from a synthesis model by Alessandro Marconi. But, well, so what's the idea? Well, the idea is that feedback explains this very naturally. So let me give you the very quick argument, which is a reincarnation of many older arguments. So how does quasar feedback regulate black hole growth? Well, a good theoretical explanation should be simple and minimize the number of free parameters. And what it makes me optimistic about this having something to it is that you can do the entire derivation in 3 lines with no free parameters. It might be more impressive to your colleagues if the derivation takes 45 pages, but it's also exponentially more likely to be wrong. So you have a bright quasar, your light bulb, and it's shining. That exerts some radiation pressure on the gas, some outward force. And in fact, the hydrodynamic things that are coming out of the accretion disk, like broad absorption line winds and jets, also very crudely dimensionally will scale similarly. So you've got some force that scales like L over C. It's just a momentum flux coming out. And if it's accreting at the Eddington rate, L is just the black hole mass times C squared divided by the saltpeter time, which is just determined purely by fundamental constants, the cross-section for electron scattering, et cetera. Now, the force of gravity in the galaxy that this thing goes out into is just gmm over r squared. And if we note that gm over r is just the velocity dispersion squared, this sigma, you can rewrite this as the gas fraction times sigma to the 4th over g. You say, aha, the black hole grows until the radiation force outweighs gravity. I set those equal, and I get black hole mass goes as constants times velocity dispersion to the fourth. And you actually plug in the numbers, and it's remarkably spot on. I mean, the fact that it's even within orders of magnitude is really remarkable here. You'll often see this derivation done in terms of energy, and then you have to invoke some efficiency. I think the momentum argument is probably a lot more compelling, especially given that under most conditions, the centers of galaxies can radiate energy very efficiently. So probably momentum conservation is more important than energy conservation. So this very naturally suggests a picture which has been around for a long time. This is just a slight dressing up of things, of ideas that go back to Dave Sanders and others about how black holes might play into a sequence of galaxy evolution. So in this toy scenario, you go through time around here, and this is just an illustration of how the star formation and black hole growth for a galaxy going through a violent episode might look. So it spends some time more quiescently growing, not much interesting from the quasar side happens, and then maybe there's a merger, maybe there's some other violent event. I've been to way too many conferences where the entire conference is it a merger or is it a series of sufficiently large clumps slamming into each other in the center of the galaxy? The black hole doesn't care. Something violent happens that torques the gas strongly and forces it down to the nucleus. You have dense, obscured phases where you power bursts of star formation and buried black hole growth. Eventually, you hit this limit, and radiation starts blasting away the shroud of dust around it. You can see it potentially as an optically unobscured quasar, if you're lucky enough and on the right sight line. And then you clear away the material. You've quenched star formation, at least in the short term, and the galaxy starts to redden as a dead elliptical. And then perhaps in these late stages, you have some ongoing little trickle of activity that heats up the gas in the galactic halo and allows it to suppress subsequent inflows. So what does that look like in the actual simulations? Well, here's the state-of-the-art 8 years ago. Two galaxies colliding where you put in essentially the simplest toy model you can think of for black hole feedback. You say, very crudely, the accretion rate onto the black hole is proportional to the density on my resolution scale, which here is like hundreds of parsecs. So we're by no means resolving the actual accretion physics. And then you say, some number proportional to that gets dumped back in the medium as momentum or energy. The important thing is, as these galaxies merge, you go through basically the exact story I just outlined. You channel gas into the center, you have this starburst, and then in these final stages, the black hole grows sufficiently big, and it blows away this envelope of gas, and you have this little tiny surviving disk, but you've essentially cleared out the medium. And nowadays, simulations have improved a lot. We can zoom in, and this is now a simulation with sub-parsec resolution around a black hole, looking at the dynamics in that central medium right when the black hole is about to hit that critical mass. In the left case, we follow all sorts of messy ISM and stellar feedback physics, but we don't include any feedback from the black hole. In the right case, we just say that proportional to the accretion rate out of the central tenth of a parsec, the resolution length, so you can think of it as very crudely the outer size of the viscous black hole accretion disk, a high velocity wind gets launched out. You could argue that maybe the high velocity wind isn't the most interesting feedback component, and I'll come back to that, but the point is, you can see it just completely changes the nuclear dynamics, very efficiently blows away this nuclear disk that otherwise just keeps chugging along and powering more and more and more black hole growth. So when you look at the results of those kinds of simulations, what you find, and this was shown by Tiziana Di Matteo and many others since then, is that you can nicely reproduce these observed relations with essentially the full-blown simulation version of that simple analytic scaling. So these black points are observed M sigma data, and these are different simulations with that sort of simple toy model of feedback. The important thing is that not only do you get a reasonable relation, but also if you don't include feedback, not surprisingly, the black hole just runs away in these dense accretion phases. As far as the galaxy is concerned, the black hole is sufficiently small that it doesn't really matter to the galaxy whether it grows up to its sort of M sigma mass or 10 or 50 times that mass. Now, I think something this area often gets criticized for is the lack of actual predictions, and I just want to defend myself and fellow theorists a little bit on that and actually say that there have been a number of actual predictions that have come out of this kind of modeling. It's not entirely post-diction or explaining observations we already knew were there, You could argue that the m-sigma relation itself was predicted, although there were certainly already hints when Stilk and Rees, 98, wrote their paper that there was a correlation between black hole mass and galaxy properties. There's a number of other predictions that have been made. So, for example, we heard about evolution in the black hole host galaxy correlations. Some of the very first papers on this, myself, but others actually quite a bit earlier, had pointed out that high redshift galaxies were already known to be much more compact. You take the same mass galaxy, make it a lot more compact, the binding energy, the escape velocity goes up, your black hole has to get bigger to pump in enough energy to unbind the material. So the trivial argument I gave you at the beginning of the talk requires that the ratio of black hole mass to galaxy mass goes up by, factors of a couple at the redshifts 2 to 3. There's also, a whole literature on predictions that things like pseudobulges should obey different correlations, for example, that were actually predictions. And I just say that because it's very rare in this field. I also bring this up just to make the point, a very common misunderstanding is people say if black hole masses relative to galaxy masses were bigger at high redshift, that means that black holes grew before their galaxies, as if that implies some very, magic channel that happened at high redshift where black holes grew independent of galaxy growth. This, at least in this scenario, doesn't mean that at all. It just means that, it grew along the same exact story I just described that might apply better to low redshifts, where some dynamical disturbance pours pours gas in until the black hole gets big enough to blow away material. It's just that, the critical mass was a little bigger at high redshift for the same galaxy mass. And then the galaxy can accrete some fluff low redshifts. But, it's not actually that exotic of a scenario. And another thing that comes out very naturally from these self-regulated, feedback-driven models is coevolution of galaxies and black holes. So we heard a lot about downsizing in the black hole and galaxy populations, and the remarkable observational fact that's shown on the right here from Andrea Merloni's work, showing the star formation rate density of the universe and the black hole accretion rate density multiplied by some factor, and how they evolve very similarly. This is showing the black hole mass that corresponds basically to the knee of the luminosity function, downsizing at lower redshifts. I've worked a lot on this myself, and I think the depressing conclusion is at lowest order, all this tells you is that self-regulation happens, because these are very integral numbers. So basically, as long as the black hole mass is pegged in this sort of upper limit sense to galaxies, and as long as there is sort of sufficient violence over a Hubble time for an average galaxy for the black hole to see some events, it's going to catch up, and you're going to get these correlations independent of any of the actual details about what specifically fuels black holes. So this doesn't, at lowest order, really tell us anything about how individual black holes grow, which is a little unfortunate, although it does at least back up this feedback story. Now, there's lots of other things that the theorists like that AGN feedback can do for you. So I mentioned this idea that it can heat up the halo and suppress subsequent star formations. This is from work by Volker Springel showing galaxies after a merger. You see the temperature here. You can much more clearly see the shock wave from the AGN going off, propagating out through the halo, heats the entire halo up to supervirial temperatures. Actually, you end up unbinding something like half the mass of the galactic halo by just heating it up. And you dramatically suppress the post-quasar star formation for a couple gigayears. This also puts a lot of metals out into the medium. I think this movie might not be working, but that same shock wave is going to launch out a lot of metals. And various people recently in a series of papers, Ian McCarthy and Joop Shea and their collaborators, have argued that this can explain things like the entropy profiles of groups and clusters, as well as their metal abundance gradients. This is the evolution of some cluster showing the gas temperature, or some large group, and how AGN feedback heats that whole thing up at early redshifts. And using the same simple models, you can actually get a remarkably good agreement with a lot of the observations. And AGN have been invoked through this channel to be the sort of mysterious source of preheating that people doing large group and cluster work like to invoke to explain various properties. Now, when you ask where AGN feedback becomes important, there's actually a pretty clear trend as a function of galaxy mass as to whether or not you care about AGN feedback or how much you care. So these are all different models. I didn't bother labeling them. They're different semi-analytic or simulation calculations. The important thing is essentially everybody's models agree that normalization is a little bit arbitrary. But what's plotted is the ratio of the energy that's being put into the medium by black holes relative to star formation as a function of halo mass. And you can see this is 1 right here. So basically, stars dominate the feedback if your points are below here, and black holes dominate it above here. And there's a clear transition mass, which is about 10 to the 12 in halo mass, where this trades off. And this arises for many reasons. One, because of the scaling of black hole mass with galaxy mass, but also simply because star formation is strongly suppressed in halos above this mass. And that happens probably for cosmological reasons. Feedback helps with that, but that's to some extent just built in from the nature of galaxy halos. More massive halos, the cooling time of the halo is longer than the dynamical time, so you don't have this incredibly rapid accretion happening on a dynamical time of gas onto the galaxy. So you transition from being sort of star formation dominated to AGN dominated. And again, you could derive this from a number of different angles, but you could argue that it's just a binding velocity will give you essentially the same thing, right? If you take the fact that stellar feedback has difficulty, you can't drive a wind using stellar feedback at more than a few hundred kilometers a second. That'll tell you right away that these most massive halos can't be strongly affected by stellar feedback, whereas AGN can, of course, drive winds at 30,000 kilometers a second in principle, so it can affect very, very massive halos. So the idea is this massive end is where you have inefficient star formation and you invoke your black holes, but you'll notice that I haven't really explained how that inefficient star formation is maintained. I sort of alluded to it very briefly at the beginning, but again, we have a movie that doesn't want to work, but basically, this leads to a critical distinction that's widely discussed in the literature on feedback, but I think is not entirely appreciated by people who don't spend too much of their time thinking about this. So when people say AGN or quasar feedback, they often mean one of two very different things. And if you'll forgive me for perhaps being a little pedantic, I want to make it very clear what these two forms of feedback are. So you'll often hear them called quasar mode and radio mode, which are terrible terms for several reasons. There's actually no reason to think that this is uniquely associated with quasars, that this is uniquely associated with radio jets, or that radio jets don't do most of the work here. So I think a better term, although it's frankly lost the historical battle for what people will use, is transition versus maintenance mode in terms of telling you what they're supposed to do. But the idea is that this transition mode feedback is associated with high accretion rate stages, and it's the feedback that you invoke to potentially move galaxies from being blue to red, to blow out gas. Since it's associated with high accretion rate phases, it has to act rapidly, since those phases don't last for Hubble times. They last for sort of 10 to the 7 years, perhaps. If you're trying to blow out gas, if you're acting at high accretion rates on small time scales, the corresponding spatial scales where this is going to be dynamically relevant, where essentially the dynamical times are compatible with this, are going to be small. So it's going to act on maybe kiloparsec scales, maybe parsec scales. Since we're talking about high accretion rates, this may be associated with violent events, maybe mergers, maybe violent clumpy disks, etc. But really, the important thing is that this is the feedback invoked to regulate the black hole mass. Black hole mass growth happens at least largely in high Eddington ratio phases. Therefore, whatever stops black holes from growing and ends them up on m sigma has to control the high Eddington ratio phases of their growth. So it has to be associated with these rapid stages. Now, on the other hand, this maintenance mode of feedback is associated with low accretion rates. And the idea, theoretically, is that this is what keeps galaxies red once they have turned red. The important thing is low accretion rate phases are ubiquitous. Now, the duty cycle for that is basically 100%. They're on for a Hubble time at some low Eddington ratio. And in principle, this doesn't have to involve any sort of morphological change. But what it does have to do is act on very large scales. So what you're invoking is it doesn't have to be a violent event, you just are invoking some steady state or on intermittent trickle of gas that can somehow launch feedback out that will affect the galactic halo. Now that theoretically is a big part of the motivation for why people associate this with radio, because of course radio jets can and do punch well out of galaxies and get way out into the galactic halo. So that's certainly a very compelling possibility for the mechanisms here. But people have also talked about winds from low radiative efficiency systems being the culprit here. But the important thing is, whatever heats up galactic halos and solves your essentially classical cooling flow problem is what regulates galaxy mass. Because the galaxy mass problem comes from the late time cooling of this gas out of galactic halos. Not from the little bit of mass that was left over at the end of the galaxy merger that you saw in that movie, the Quasar blowout. That was like 10% of the galaxy mass. I can shift my galaxy masses by 10% easily. No problem there. If you believe my galaxy mass is in any model to 10%, you're kidding yourself. So this is really what we think needs to regulate the galaxy mass. So this radio mode is, of course, at least something we have a strong observational handle. I'm not going to talk about the observations very much, and I think Nahum will talk more about the observations that I would associate with the quasar or transition mode tomorrow. But there's at least a couple of compelling observations that line up with a lot of these theoretical ideas. One is the observation that radio loudness seems to anti-correlate with Eddington ratio, which is actually a fairly natural consequence of accretion disk theory if there's a state change into some thicker radiatively inefficient disk at sufficiently low accretion rates. But I think it's still quite up for debate whether that happens in supermassive black holes or if that transition is the same. Even more remarkably, especially given how tight this correlation seems to be, there's this plot from Allen et al., and there's actually been a couple of follow-up works to this, that attempts to observationally estimate the Bondi accretion rate, just for measuring hot gas properties near the black hole, and compare it to the jet power, and also compare this, unfortunately I don't have the three-dimensional version of the plot, to the cooling luminosity and cooling flow halos. And all three of these quantities seem to just line up right on top of each other, suggesting that everything's in some sort of steady state equilibrium energy balance. The agreement is frankly too good for me to think there's not something weirder going on here, but it's certainly compelling. Now I think there are still questions about what in that radio mode is the dominant, again we have a movie that doesn't want to work, sorry about that, is the dominant form of feedback. Is it giant radio jets or is it these more quiescent bubbles? So of course there's Perseus, which is a great example for giant cavities, etc. But actually, the theoretical problems that people are trying to solve kick in as soon as you cross this break in the galaxy mass function. So a lot of the interesting work might happen in smaller ellipticals and in their X-ray halos. And in fact, if preheating is important to this, that's where it's going to happen, basically, is shock heating these halos and getting material out of them. So at the risk of repeating myself, this is just a little cartoon to illustrate the toy model idea here that we have. So here's a couple of galaxies merging. Here's their position on the AGN luminosity function. And here's the instantaneous power input and integrated energy from feedback from three different sources: stars, the so-called quasar mode, and the so-called radio mode. So early on, and for a Hubble time before here, say, stars dominate. Then the quasar has its very brief day where it dumps a bunch of energy, shock heats everything. There's a lot of energy contributed by that, comparable to the input energy from stars over the entire lifetime of the galaxy. And then you have this trickle of accretion at low Eddington ratios that heats this halo or maintains it in equilibrium with the cooling flow. So it's a relatively low rate, and in fact, it doesn't need to be anywhere near dominant in the total energetics of the AGN over its lifetime in order to balance cooling. And you can translate that into ideas, admittedly speculative, about where these different systems would live on, say, the luminosity function as a function of their evolutionary stage. So way down here, you might have these dead bulges that are accreting from their hot halos and maintaining their systems, and they might not even be visible optically if they're radiatively inefficient. you've got Seyferts, which are your stellar disks that are puttering along, or stellar feedback-dominated disks. And then at the bright end, you've got these rare violent episodes. So everything I've said up to now is pretty hand-wavy, I admit. And frankly, that's the state of most of the work in this field. But I would regard it as a proof of concept that this simple idea about AGN feedback can resolve a lot of problems. So that doesn't mean that this is the end of the story. And for my last few slides, I just want to say where things are going from here. And this is work I've been involved in, but a huge number of other people in this field are working on dramatically improving what I just described and really making it a physical predictive model, not just a sort of toy model that we can illustrate does interesting things. But there's at least 3 major avenues that people are pushing on, all of which ultimately need to happen simultaneously for us to get to fully predictive. The first is, of course, people are working on improving the modeling of the ISM, its structure, the feedback from stars. I apologize again for this not working, but the simple point I was trying to make was this is a slightly more realistic model of the ISM than you saw in that earlier movie where the gas was all just smooth, right? It's some turbulent, messy medium with little cloudlets floating around, et cetera. And this is the medium into which AGN propagate their energy and momentum and light, et cetera. This is the sort of state-of-the-art of the models, both in simulations and in analytic treatments. You'd be disturbed how much the treatment in simulations really is essentially collapsing this down to its one-line form, basically. Those are not the same. And in fact, the lesson that's been told to us by a huge community who've worked on this problem for the normal ISM with stellar feedback is that these sort of different mechanisms of feedback, these different processes, are very nonlinear, and they interact very nonlinearly. So you can't simply take your idealized quasar model and paste it on top of your idealized galaxy model and expect that to be a good representation of reality. This is a lot more difficult problem to deal with. The second aspect that's improving rapidly is, of course, attempting to follow accretion consistently in this whole model. So thanks to Moore's law, as well as numerical actual algorithm improvements, we can start to directly follow inflow from galactic scales down to subparsec scales. Maybe not directly, certainly a ways away from the Schwarzschild radius, but at least into radii where you'd actually call it the sort of Shakura-Sunyaev viscous disk. And this is one example of a simulation that starts at a kiloparsec and has subparsec resolution. You can see these fairly chaotic flows near the center. This is a star cluster that's launching off little winds, and it gets messy quite quickly, and this is just sort of looking at the accretion rates on different scales through that simulation, where you see the inflow going from kiloparsec scales down to fraction of a parsec scales. And I'd say, again, there have already been a couple of key lessons from this from all the various people who've worked on it. For example, one obvious lesson, but nevertheless worth confirming, is that accretion onto black holes, especially at high rates, has nothing to do with Bondi-Hoyle accretion, which sounds obvious. Gas has angular momentum. It has tremendous amounts of angular momentum compared to what it needs to have to accrete, but Bondi-Hoyle is still our default assumption in most of these models. But it's also, by no means on these large scales is it the sort of opposite assumption. When people don't assume Bondi-Hoyle, they tend to just assume it's a Shakura-Sunyaev disk all the way out to, 5 kiloparsecs, which is also a totally incorrect assumption. You can see here, it's these very strong global instabilities, and we already heard about this discussed in other contexts. You have these things like bars, and here you can see it's bars within bars within bars, and in fact, it's bars all the way down. Now, more accurately, a lot of these aren't bars. They're m=1 modes, they're clumps, etc. It's non-axisymmetric features all the way down. That's not very charming, so following on bars within bars, I just like to refer to it as stuff within stuff. But there's a whole cascade of gravitational instabilities that dominate accretion, from galactic scales at least down to what we'd think of as the traditional accretion disk. And people are only just beginning to parameterize that. I'll skip the gory formula because, frankly, it's early stages yet on understanding that. Now, finally, of course, if we want to understand feedback, we want to put in the actual feedback. So the other thing that's starting to happen is people are putting in the actual feedback physics self-consistently. Now, the real challenge here is, unlike studying the ISM and stellar feedback physics, we don't have a stellar population model, we don't have a stellar evolutionary track for black holes. You can't say, I have a black hole of this mass. I can know roughly what its jet power is and when the jet's going to turn on and what its winds are going to do a priori. You have to make a lot more assumptions. So this is slower going for that reason, among others. But we at least have a list that we're thinking about that many people are working on of what the relevant mechanisms are. And there's, of course, radio jets, which I've talked about. There's radiation pressure. That was the original argument I gave. Given that AGN are much brighter than stars in the brightest quasar phases, sort of by definition, this should be dynamically important. And there's accretion disk winds, about which I'm sure we'll hear a lot more, that we know exist. So the frontier is putting these in self-consistently with the other tweaks that the other improvements that I just described. Now, much of the challenge, and this is my last slide just to show, this is a cosmological simulation showing the stars and gas. Here the green is warm ionized gas, the red is hot gas at greater than 10 to the 6 Kelvin, and the magenta is molecular gas in a forming Milky Way as a function of time. And this has a model for stellar feedback and a model for AGN feedback. Now, admittedly, I'm not giving you all the information, but I think the real challenge in going forward and making observational predictions is tell me where the AGN's dominated and where the stars are dominating. How do we pick out in this mess something that gives us a robust diagnostic of how the AGN feedback is changing the galactic structure that we could hope to distinguish from how other forms of feedback are operating? And that's, I think, a really challenging question for the future. So, thank you very much.
Most of the X-ray background sources must be in the maintenance mode. Then because most of them are absorbed, I think the maintenance mode must involve a certain amount of cold gas. I mean, you cannot just have hot gas. So
yes.
How does that fit into...
That's an excellent question. And I think it also fits, I think the maintenance mode does have to involve cold gas. I think this idea that you just sort of accrete Bondi Hoyle out of the sort of central peak of the hot dark matter halo gas profile doesn't work at all for many reasons. And in fact, there's also the observational fact that there's a very close correlation between the jet systems and the cooling flow systems and the presence of cold gas in these systems. So it has to involve cold gas. Why some of these apparent correlations between the Bondi power and the jet power work, if that's the case, are puzzling. And, you know, moreover, how that can work, given that just introduces one more step at which you degrade the degree to which the black hole would know anything about the halo. So, you know, I don't really have a great answer to that. It's a real challenge. I think, you know, some of the solution is almost certainly that this isn't, you know, a sort of stable equilibrium system. It probably overshoots at some times, and you dump too much power in, and you sort of quench for a while, and you oscillate back and forth. But
if on large scale the gas comes in from the cosmic web, then you could imagine that not all, I mean, the HN is not able to ionize all that power, and you get pockets of cold gas.
Sure, yeah, it's not hard to get pockets of cold gas in. It's, of course, hard to get them down to the black hole at a very high rate, where you need to invoke something like galaxy mergers or violent disturbances. Fueling a Seifert or fueling, you know, this maintenance mode is not very challenging if you have any gas supply in the galaxy. You essentially need, you know, one molecular cloud every couple hundred million years to get to land inside the black hole radius of influence. So a molecular cloud randomly hits the central 10, 20 parsecs of the galaxy, and you're in business. That may not be the dominant channel, but that's one example.
One important thing left out of your discussion, in particular the transition mode feedback, is the stellar mass loss from evolution of the young star population, which will return roughly 30%
Yes.
of the stellar mass into the interstellar space in the center of the galaxy.
Yes.
So it's not as simple as turning the quasar on, getting rid of the
Yes.
existing ISM. You also need to keep the galaxy red.
Yeah, yeah. So there's I think, you know, there might be, now whether you'd call it maintenance mode or transition mode is maybe a little arbitrary, but you make a very good point. Even if you perfectly solve the cooling flow problem, which I can do in a simulation just by having no gas in my halo, it's an easy way to do it, and you get rid of all your gas at the moment of a merger, you have this problem of this mass loss trickle, which, if you don't do anything about it, is enough to already make your galaxy too blue compared to the observations. So you need to be doing something to either heat or expel that gas. There's a nice series of papers by Luca Ciotti and Jerry Ostreicher about this, but I think that's another area that needs to be looked at in more detail.